Hey guys, in this video I'll be talking about one of the classic results about connectivity in graphs. This is given by Menger's theorem, which is proved by Carl Menger in 1927. Now previously we have looked at the notion of connectivity in terms of vertex cut. Remember, the connectivity of a graph is just the minimum size of a vertex cut of the graph. We also have the edge version of this, namely, edge connectivity is defined in terms of the size of a edge cut. In particular, the edge connectivity of a graph is just the minimum size of an edge cut. Now, Menger's theorem gives a different characterization of connectivity. Namely, connectivity will be expressed in terms of the multiplicity of disjoint paths. And for that matter, the edge connectivity will be expressed in terms of the multiplicity of what we call edge disjoint paths. So before we give the precise statement of Menger's theorem, let us clarify some of the terms that we are going to use. Well, first of all, let me begin with the following definition. Suppose we have two distinct vertices of a connected graph G. Let's call them X and Y. So imagine we have two vertices here in the graph G, which are fixed. Then two XY paths are called internally disjoint if they have no vertices other than X and Y in common. So one way to imagine these paths is that except for the starting point and the ending point, or rather the terminal points, X and Y, then none of the internal vertices of the paths are the same. So if this is one of the XY path, then another path that looks something like this, which doesn't have any internal vertices in common with the previous one, is said to be internally disjoint from the previous one. So these two paths are internally disjoint. Let me give you a more concrete example. Suppose we have the following graph here with the vertices xy identified. How many internally disjoint paths are there between x and y? Well, for example, we have an xy path using this edge, followed by this one, and this one, and this one. Another path would be this one here using the blue edge, followed by this one and this one. So these two paths are internally disjoint because they do not have any internal vertices in common. Now notice that any two xy paths which are internally disjoint must use different edges coming out from x, for example. And the fact that there are only two edges coming out from x, and we have found two internally disjoint paths, the maximum number of internally disjoint paths from x to y in this graph is just 2. All right? Anyway, let us now move on to the other definition, which will be required for Menger's theorem. Well, this time, we say that two xy paths are edge disjoint if they have no edges in common. So unlike internally disjoint paths, we now do not require the internal vertices of the paths to be different, but rather we want the edges to be different. Let me give you one example. Suppose we look at the two distinct paths just now. Well, these paths are internally disjoint but they are also edge disjoint. This is true in general. Every two xy paths which are internally disjoint will not have common edges, and therefore they must be edge disjoint. However, the converse is not true. For example, if we take the following xy path given by the green edges, clearly the path with the red edges and the path with the green edges are edge disjoint because none of the edges are in common. However, these two paths are not internally disjoint because they share a common vertex, which is the vertex here in the middle. Alright, next we're going to look at the notion of vertex cut and edge cut with two vertices identified. So as before, suppose we have two distinct vertices, x and y, in a connected graph G. We say that a set U of vertices is an xy cut if x and y are in different components of G minus U. In other words, after deleting U from the graph G, the vertex x and y will be in different components. This means that the vertex x and y must survive the removal of the set U from the graph G, which means any xy cut should not contain the vertex x or the vertex y. Likewise, a set F of edges is called an xy edge cut if x and y are in different components of G minus F. Let me give you some examples. So here's the graph we saw just now, this time with the other vertices labeled as A, B, C, D, E. Let's consider the set U consisting of the vertex C and D. Clearly, deleting the vertex C and D from the graph, the vertex x and y will be in different components. So this is an example of an xy cut. On the other hand, if we take U to be the set consisting of B and D, then this is not an xy cut, since after deleting B and D, the vertices x and y are still connected. Alright? What about edge cuts? Well, here are some examples. Let's suppose we take F to be the set consisting of the edges AC, CD, and DE. Now clearly, by deleting AC, CD, and DE from the graph G, x and y will be in different components. So F is an XY edge cut. Indeed, we can find a smaller edge cut. For example, if we take the set F to be, let's say, the set consisting of XA and XD. After deleting AX and XD from G, the vertices XY will be in different components. This is another example of an XY edge cut. Indeed, this one is smaller because there are only two edges inside F, as compared to the one just now, which has three edges. Anyway, let me show you now an example of a set of edges which is not an edge cut. Let's take, let us take F to be, let's say, the set consisting of CB and CE. If we were to delete the edges CB and CE from the graph, the vertices XY will not be disconnected, since there is still a path in the resulting graph connecting x and y. So this f here is not an xy edge card. Do you follow me? Alright, to state Menger's theorem, we shall require the following terminology and their respective notation. First, we have lambda xy, which denotes the maximum number of pairwise internally disjoint xy paths. So here, the vertices xy are fixed in the context. Alright. Also, lambda prime xy will denote the maximum number of pairwise edge disjoint xy paths. Likewise, kappa of xy will denote the minimum size of an xy cut, whereas kappa prime will denote the minimum size of an xy edge card. One way to remember this notation is that the prime version, the lambda prime and the kappa prime, corresponds to the edge version of disjoint paths as well as edge cut. Okay, we are now ready to state Menger's theorem. Alright, there are two versions of Menger's theorem. Here's the vertex version. So suppose we have two distinct vertices x and y in a connected graph G such that xy is not an edge of the graph. Then Menger's theorem says the minimum size of an xy cut is equal to the maximum number of pairwise internally disjoint xy paths. So in short, this is given by kappa of xy being equal to lambda of xy. So that is the vertex version of Menger's theorem. Okay, here's the edge version of Menger's theorem. Again, suppose xy are two distinct vertices in a connected graph G. But this time we do not require that xy is not an edge of the graph. You see, previously in the vertex version, we do require that xy is not an edge of the graph. But there's no such restriction in the edge version. Anyway, Menger's theorem says the minimum size of an xy edge card is equal to the maximum number of pairwise edge disjoint xy paths. In short, this is given by kappa prime of xy being equal to lambda prime of xy. So that is the edge version of Menger's theorem. Now the proof of Menger's theorem will be given as a consequence of our result for network flow that we are going to encounter in subsequent chapters. So for now, we're not going to give a proof of this result. Instead, we will just take this for granted and apply this to some examples. Okay, let me now give you some instances of Menger's theorem. Let us consider the following graph G with the vertices xy identified. Notice that the vertices xy are not joined. So xy is not an edge of the graph G. Well, this condition is required by the vertex version of Menger's theorem. For convenience, the middle vertex is labeled as A. First of all, notice that any xy path will have to go through the middle vertex A. Therefore, there can never be two pairwise internally disjoint xy paths. This means that the maximum number of internally disjoint xy paths is just 1. This implies that lambda of xy is equal to 1. What about the size of an xy cut? Well, notice that the set consisting of the vertex A is an xy cut. This is because x and y will fall into different components upon deleting the vertex A. Hence, the minimum size of a vertex cut must be 1. And that means kappa of xy is 1. So for this graph, we have kappa of xy being equal to lambda of xy, as expected from the vertex version of Menger's theorem. Okay, using the same graph, let us now illustrate the edge version of Menger's theorem. First, let us look at the number of pairwise edge disjoint xy paths. Well, the maximum number of such paths is given by lambda prime of xy. Notice that there are 3 edges going out from x, and any path from x to y must use one of these edges. Since we are considering edge disjoint paths, the number of edges joined to x will give us an upper bound on the number of pairwise edge disjoint xy paths. So lambda prime of xy is at most 3. On the other hand, we can actually find 3 pairwise edge disjoint xy paths. Namely, we have the path xbacy given by these red edges. Also, we have the path xay given by the green edges and does not share any common edges with the previous path. Finally, we also have the path xdaey given by the purple edges, which again does not share any common edges with the previous 2 paths. So we have found 3 pairwise edge disjoint xy paths. So altogether, this implies that lambda prime of xy is equal to 3. Alright, so let us now look at the size of an xy edge cut. Well, it's not difficult to see that deleting any 2 edges from the graph will not disconnect the graph. This means that the minimum size of an xy edge cut given by kappa prime xy must be at least 3. Okay, because deleting any 2 edges will not create components, will not create more than 1 components. On the other hand, we are able to find a xy edge cut of size 3. Namely, if we take F to be the set of edges consisting of, let's say, BA, XA, and DA, then the graph G minus F will fall into components, and the vertex X and Y will be in different components. So note that X and Y will lie in different components in the graph G after deleting these edges in F, which means F is an XY edge cut. Well, this implies that the minimum size of an XY edge cut is bounded above by the size of F, which is 3. So kappa prime of XY is at most 3. Now, together with the previous lower bound for kappa prime, which is 3, we conclude that kappa prime of xy is exactly 3. Okay? Previously, we have shown that lambda prime of xy is also 3. Therefore, this is an instance of the edge version of Menger's theorem. All right? So the conclusion is kappa prime of xy is equal to lambda prime of xy as expected from the edge version of Menger's theorem. Alright guys, I suppose we have some idea of Menger's theorem up to this point, and we're going to do some examples later on in the next video. So please stay tuned. Thank you.